This webcast talks about the friction force and dissipated energy. Friction is a force that resists the motion of one object sliding past another. It always points in a direction that is parallel to the two surfaces that are sliding against each other, but that points in the opposite direction to the way that the objects are trying to slide. Friction depends very much on the materials of the two objects that are sliding against each other. Friction can be both useful and harmful. So some of the many useful ways that friction is that if you put a picture in the wall, friction is what holds the nail in place. Friction allows the tires of a car to grip the road. Friction is the reason that we can walk around without tipping over, without falling over. But friction can also be harmful. Because friction causes the two objects that are sliding against each other to heat up, that heat can cause problems. For example, it causes wear and tear in the engine pistons that move up and down inside the engine, and in other mechanical machinery. So we have ways of reducing friction, primarily by lubricating a surface, applying Teflon to it or some type of oil or lubricant. Friction is caused because there are tiny bumps and protrusions on the surfaces. They may not be visible. Even a surface that seems very smooth has these small protrusions. You could consider these to be similar to Velcro. In a Velcro fastening strip, one side has hooks and one side has loops. And when the two surfaces connect with each other, those hooks and loops join together, and it makes it very difficult to try to slide one of those strips against the other. Every object, when you try to slide it against something else, behaves in a similar fashion. For example, here we have a piece of metal foil, and it looks very smooth and shiny and slick. But if you magnify down on the surface, you can start to see that there are little mountains and valleys. These are at the microscopic level, at the level of individual molecules and atoms, and so it is not perfectly smooth, and these small little bumps in the surfaces can catch on and attract the bumps on another surface, and that's what causes friction. Let's think about an observational experiment. Let's say that we put a block on a table and it just sits there. We've done force diagrams for this situation before, and we know that this block is just at rest. The net force is 0. There is a gravitational force, that is the Earth, attracting the block and trying to pull it toward the center of the Earth. And then the floor is supporting the block, and that is called a normal force. And those two forces, the normal force and gravitational force, balance each other so that the block does not move. What if we applied a small force trying to pull the block to the right? But initially this force is very small and the block does not move. Well, since it does not move, the net force again is 0, by Newton's first law. So we still have the same normal and gravitational forces, but now there's an applied force on the block. Someone is pulling the block to the right. Something has to be balancing that applied force. It's being balanced by the force of friction. Friction points to the left because it is opposing the motion, and the friction force is enough to balance the applied force so that the net force is zero. In this case, we would call this friction force static friction, because the block is stationary, it is not moving. What if we applied a little bit larger force on the block? We're still trying to pull it to the right with a greater force this time, but the block still does not move. So now we notice that the applied force is bigger, but so is the friction force. It has gotten bigger. The block is still not moving. This is still a static friction force, but the static friction has increased and is still balancing the applied force. Okay, and then the final scenario, let's apply an even bigger force to this block. And now the block does begin to move. Okay, the block is sliding to the right. So now we have a situation where the applied force is large enough to overcome friction, and there is still friction that is opposing the motion as the block slides against the floor, but now we would call this a kinetic friction force because the block is in motion. So, reviewing those four scenarios, we are observing that static friction can vary, and it up to some maximum value. So when you first start pulling an object against another, it will initially not move until the applied force gets large enough to overcome this maximum value of static friction. So static friction, we call it static friction. The root of that word static is the same one as in the word stationary. So static friction is the friction force that opposes sliding when there is no motion. So static friction balances the pushing force until the object begins to slide. Static friction is always just enough to balance the forces that are pushing the object, and so static friction can vary in its strength up to some maximum value. And so look at the formula here. We have the friction force with an S subscript that represents static friction is less than or equal to mu sub S times the normal force. The mu sub S, mu is the Greek letter mu, that is the coefficient of static friction, and friction force is calculated by the coefficient of friction multiplied by the normal force. Notice that friction is proportional to the normal force, not to the weight or the force of gravity on the object. If the pushing force exceeds the maximum static friction, the box will begin to slide. So as the box is sliding, it is still experiencing friction, but now the friction is called kinetic friction. Kinetic is related to the Greek word that means motion. And so kinetic means friction during motion. Often we might want to calculate the maximum amount of static friction using the formula that we just saw, mu sub S times the normal force. So the coefficient of static friction times the normal force would be the maximum amount of static friction. If you apply a pushing force that is larger than that, then the object will begin to slide. So that would tell us how much force we need to apply to get the object to move. Okay, so let's look at example 1 here. Sam needs to push a 100-kilogram wooden crate horizontally against a plywood floor, and the coefficient of static friction is 0.5. So how much force would Sam need to apply to start the crate sliding? Well, we know the mass and the coefficient of static friction. And if we did a force diagram, these would be the forces on the crate. Okay? So there is no net force in the vertical direction. And so in this case, our normal force is equal to the gravitational force, which is the weight of the crate. You know, the 100 kilograms times 9.8. And the crate will begin moving when the applied force exceeds that maximum static friction force. So we can find the maximum static friction force as the coefficient of static friction times the normal force, which would be 490 newtons. So any force that Sam applies that's bigger than 490 newtons will cause the crate to begin sliding. Okay, once the crate begins sliding, it's in the realm of kinetic friction. Kinetic friction is the friction force that opposes sliding when the objects are moving. Kinetic friction is constant. Remember, the static friction was variable up to some maximum value, but the kinetic friction is constant, and it equals the coefficient of kinetic friction times the normal force. So the formula for calculating friction force is the same in both the kinetic and static realms. The only difference is whether you use the kinetic coefficient of friction or the static coefficient of friction. Here's a table that gives you some sample coefficients of static and kinetic friction. Now, friction depends very much on the two surfaces that are touching each other, what material they're made of. And so these have to be found experimentally, and so you would have to look them up, or they would have to be given to you. You do not need to remember any of these coefficients, but this is just some sample ones so that you can look at them. Notice that there are no units on the coefficients of friction. If you look at the formula, if you solved for the coefficient of friction, you would have the friction force divided by the normal force. The two forces both have the same units of newtons, and so those units cancel, and the coefficient of friction is a dimensionless quantity. It has no dimension. Going back to this table, I'm also noticing that most of these numbers are between 0 and 1. And so usually the coefficient of friction is less than 1. Also notice that the coefficient of kinetic friction in every case is smaller than the coefficient of static friction. Always. Okay? So if we just summarize that, the coefficient of static friction is always larger than the coefficient of kinetic friction. It takes a little more force to overcome static friction to get the object moving initially, and then a little less force to overcome the kinetic friction. Usually the coefficient of friction is less than 1, but it is possible for the coefficient to be greater than 1. When the coefficient of friction is greater than 1, that means it takes more force to make the object slide than it does to just pick the object up. So an example of that would be something like the grippy rubber, sometimes grippy rubber objects, it's almost impossible to make them slide, but you can pick them up. Also, a sticky note falls into that category, right? It's very hard to slide a sticky note, the sticky part of the surface, across a piece of paper, but you can easily just pull it off of the paper and pick it up. Okay, so here's another example. Let's say that I'm having my office carpets cleaned and I push my sofa across a carpeted floor at a constant speed. And I'm pushing with a force of 80 newtons. That's a constant force. The couch has a mass of 60 kilograms. What is the coefficient of kinetic friction? Okay, well, I would write down the things that I know, and I would draw a force diagram. I know that in this situation, the net force is 0 in both the vertical and the horizontal direction because the sofa is moving at a constant speed in a straight line. It's moving at a constant velocity. Okay, so net force is 0. That means that in the horizontal direction, the applied force minus the friction force is 0, or in other words, they're equal to each other. And so my applied force of 80 newtons has to be balanced by the kinetic friction force, which is calculated as the kinetic coefficient of friction times the normal force. In this situation, the normal force equals the gravitational force on the sofa, so it equals the 60 kilograms times 9.8. And so I can divide 80 newtons by that normal force to get the coefficient of kinetic friction. It's 0.136. Again, notice there are no units on this coefficient. It's a dimensionless quantity. So frictional force is proportional to the normal force, not the weight. That's because the frictional force opposes the motion when two objects are sliding against each other, and the normal force represents the strength of the contact between those two objects. Remember, for things that are on a ramp or an inclined surface, normal force and gravitational force are not always the same thing. So friction is proportional to the normal force. What if we had someone who could push a car along a flat road fairly easily, but she couldn't lift the car in the air? Why is that? That's because pushing the car just requires pushing with a force large enough to overcome the frictional force, whereas lifting the car requires lifting with a force greater than the weight. So the frictional force is smaller than the weight force because the friction is equal to the coefficient of friction multiplied by the normal force. And remember, that coefficient of friction is usually less than 1. It certainly would be between rubber and asphalt. So without friction, we wouldn't be able to walk very easily. And why is that? Here's a real case where friction is useful. It's because without friction, there'd be no force to counterbalance the small forces on our feet. And so our feet would start to accelerate away from us. You know, it would be like walking on a very slick surface like ice. And so we would not be able to walk well if we didn't have friction working with us. So I just want to show this simulation because I want to talk about how friction causes the molecules on the surfaces that are rubbing against each other to move faster so that they have more energy at the microscopic level. Let me see if I can open this up. So this simulation allows us to, put the objects in contact and rub them. Look how fast the little molecules and atoms start to vibrate. And the reason that they do is they get excited by this rubbing motion. Okay. So when the molecules and atoms begin to move faster, they have more energy. They warm up, right? Another example of this would be if we took someone, a skier, and we took an infrared camera so that we could look at the snow as they ski past, we would see that in the paths of where the skis are touching the snow, so the skis are rubbing it over against the snow, we get a warmer temperature along those ski paths, and that's because of friction. So friction causes energy to be dissipated. That heating of the surfaces that are sliding against each other is due to kinetic energy, motion at the microscopic level, at the level of individual atoms and molecules. This kinetic energy can't be stored in a way so that it can then be transferred again for another purpose. The energy hasn't been lost. We know where it went. But in some sense, it's wasted because that energy that has been used to cause those atoms and molecules to vibrate a little faster, it can't be transferred again to be used for useful work. And therefore, we call that dissipated energy, or E sub dis. So even though energy is conserved, not all energy is equally useful. And E dis we're going to use that to represent this unrecoverable, unusable, microscopic kinetic energy. And most commonly, energy is dissipated due to frictional forces. So the amount of energy that is dissipated depends on how long the object slides against another object. In other words, the path length. And you could calculate that dissipated energy by taking the force of friction and multiplying it by the path length. Now, we've been talking about friction, not air resistance, and they are very different phenomena. But air resistance also causes a force that opposes motion, right? Air resistance causes a drag force. And so that drag force also causes energy to be dissipated. And similarly, you could calculate the dissipated energy by taking the amount of the drag force and multiplying it by the path length. Friction and air resistance are two examples of non-conservative forces because the energy that transfers due to these two forces are non-reversible. And the amount of energy depends on the path of the object. You know, the further the object slides against another object, the more friction has to be overcome, and therefore the more energy that is dissipated.